In this video, we're going to talk about using the second derivative test to find extrema. So far, we've used the second derivative to talk about concavity. I did this in a previous video as well. This is officially where it's introduced in the textbook, so I'll go through the example problems here from the textbook on using the second derivative test for extrema. F of x is equal to 6x minus x squared is number 21. F prime of x is equal to 6 minus 2x. That makes f double prime of x equal to a -2. So it's concave down everywhere. I might just want to draw that number line for myself to show that it's negative everywhere from -infinity to +infinity for the second derivative. And what that tells me is if I'm on a concave down piece that looks like this, any critical number of the first derivative is going to have to represent a maximum point. So let's go back and find that critical number. 6 minus 2x is equal to 0. 2x is equal to 6. X is equal to 3. So picking 3 to be my point that I want to test the concavity for, f double prime of 3 is definitely -2 since there's no x value to change this. Since it's a critical number and concave down, there is a local maximum. At x equals to 3. That x value, let's go ahead and find what that maximum value is. So I need to find f of 3. It's going to be 6 times 3 minus 3 squared. For any more complicated than that, I might have used synthetic division. 18 minus 9 is 9. So there's a local max at 3, 9. Let's go ahead now and look at number 29. Give myself some more space for this one. Only a few problems with this because typically we use the first derivative test for extrema. This is just another form of a test we've already learned, and it's less common to be doing this test unless we're already finding the concavity. No need to do this test if you don't need the second derivative for something else. So let's go ahead and rewrite this as f of x is equal to 9 minus x squared to the 1/2 power. When I take the first derivative here, I get 1/2 9 minus x squared to the -1/2 power times a -2x. So that gives me half of a -2x is a -x. And I have a square root of 9 minus x squared in the bottom for my f prime of x. And my domain of this is -3 to 3, just so you're aware you can look at that, but this graph looks like this. Graph it on your graphing calculator if you want to, but it's the top half of a circle. X squared plus y squared equals 9. So it's defined from -3 to 3. So when I'm looking at this to find the critical numbers, I'm only interested in things that make the numerator 0 or the denominator 0 within that interval. So critical numbers here will be x equals to 0. We'll make the numerator 0. I'm also kind of interested maybe a little bit of 3 and -3, but not really, because there's not going to be any, I'm not going to see concavity there because there's no behavior to the left of -3 and there's no behavior to the right of 3. So I can't really call those points of inflection or anything like that. So I can't really for sure call them minimum or maximum points either in a relative sense because I need activity to the left and the right. So I'm going to just ignore those. There'll be endpoints that I'll be interested in restricting myself, but I'm only interested in this critical number that's a potential minimum or maximum right there at x equals 0. So let's go ahead and find my second derivative now. F double prime of x, derivative of the numerator times the denominator minus derivative of the denominator is, well, the denominator is this thing that we started off with. So there's its derivative right there. Times the numerator all over the denominator squared. So get rid of the square root. And so I don't like the square root in the denominator there. So I'm going to multiply by root 9 minus x squared, top and bottom, to get rid of that. So that's f double prime of x is equal to, and this gets distributed in here and here. So that's a -1 times 9 minus x squared, that the square roots will go away, minus, and then the square root will cancel here, minus x squared, because a negative, negative, negative is negative. And all that is over 9 minus x squared to the 1½ is 3/2 power. So this is a x squared minus 9 minus x squared over 9 minus x squared to the 3/2 power is a -9 over 9 minus x squared to the 3/2. It'll help me a little bit to look at the graph here to see that the square root of 9 minus x squared is always positive. So if I cube that, that's still positive. This is a negative in the top over something that's always positive. So f double prime of x is not ever going to be 0, but it is going to be, I'm going to cut it off here from -3 to 3, since that's what I'm interested in. And in between there, it's always going to be negative. It's always going to be concave down. And that tells me that this critical number there is of 0, which falls within that interval, is going to be concave down at that point, which gives me a local maximum there. There's a local max at x equals 0, my critical number, and f of 0 is the square root of 9 minus 0 squared is equal to the square root of 9 is 3. So there's a local max at 0, 3. And that makes sense because, like I said, it's the top half of the circle whose equation could be written as y squared equals 9 minus x squared, x squared plus y squared equals 9, which is 3 squared. Circle of radius 3, just the top half of a circle centered at 0, 0 with a radius of 3. So it would make sense that this point here, going 3 away from the center of 0, 0 would give me 0, 3. That all checks out with geometry. Let's go ahead and look now at number 33. Number 33 says f of x is equal to x over x minus 1. And so we're going to want to find the first derivative here using the quotient rule. Derivative of the top times the bottom minus derivative of the bottom times the top, all over the bottom squared. F prime of x is equal to x minus 1 minus x over x minus 1 squared is equal to a negative 1 over x minus 1 squared. I don't see any critical numbers. I see a vertical asymptote, but I see no critical numbers, which tells me that there should be no extreme values here. So I can just stop right there. There's going to be no numbers to stick into my relative or into my second derivative to find relative extrema. So no local, or you can use the word relative like the book does, extrema. And we can stop right there since there's no critical numbers. And that's it for this video. And let's see if that is, we'll come back next time to do some applications of this concept. Specifically, the idea of the point of diminishing returns is where we have a point of inflection, and we will be using that second derivative test possibly to help us find minimums or maximums like we did previously. So let's, we'll also be talking about the average cost of a function, the average cost function, C bar, which we have not talked about yet up to this point, but that's an important thing in business. So come back for those application topics next time. See you for the next video.